So in this video, we'll be going through the free body diagram examples of the merry-go-round. And so we're going to use the same sort of logic we did for the first two examples and apply them here. So we first want to start by drawing our coordinate system. So we're drawing it for A. It's pretty clear that we have a circle here. It's following a circular path. We're going to choose the inward direction towards the center of this circular path to be the positive R direction. We're going to choose tangent to point A and perpendicular to this R direction as the positive T direction. So the tangential direction, and that's the direction that the velocity is in at point A. And then we need to talk about a third dimension, the Y direction, because this merry-go-round's not moving up and down. So with the roller coaster example, the roller coaster was moving up and down, so there wasn't a Y direction that we had to deal with. But now there's not. We're in this fixed plane. You can imagine at a playground, this merry-go-round. It's just rotating around and it's at this fixed Y position. So we need to designate the Y direction in this case. And it's helpful to think about an arrow. So if we've got an arrow here, and then here's the back end of the arrow. The direction that's coming towards you gets represented by a point. So you can imagine the tip of an arrow coming towards you. This is what you would see. You would see a point. And then if the arrow is going away from you, you would see an X. And so this gives us a way on two-dimensional paper to add in a third direction. And so I'm going to choose the direction coming out of the page, so coming up from the page to be the positive Y direction. So now that we've defined our coordinate system, we can now draw our free body diagram for point A. So what forces are acting on the girl at point A? We've got a weight force in the negative Y direction. We've got a normal force acting from the merry-go-round on the girl in the positive Y direction. So we'll start by labeling those. So positive Y direction's just normal. So we'll call that F sub n. And then in the negative Y direction, so going away from us, or the back end of the arrow, is the weight force. And then we need one more force. Because right now, the normal force and the weight force cancel out. But we know that there's acceleration when we have circular motion. So we have acceleration pointing inwards towards the center of the circle. Looks like that. So we must be having a force pointing inwards. And so what would that force be? If I'm sitting on the merry-go-round, and this may have happened to you before, if you go fast enough, you slide off. But if you go slow enough, you stay right there. So something's keeping you on the merry-go-round. And it's very similar to what we deal with a block on an incline. So as you move an incline up, there comes a point when the block starts to move. But before that point, it doesn't move. So we apply that same thing here, and it's the force of static friction. That's what's keeping us on this merry-go-round. And then we reach a point where the force of static friction can't oppose, and we fly off. So coming over to our free body diagram, forgot to label this plus t direction, and then to the inwards is the plus r direction. So we know we have a acceleration in the positive r direction, which means we need to have a net force in the positive r direction. And that force is the force of static friction. So our free body diagram is complete. And so let's take a look at this second free body diagram example. And so you may have been confused about how to draw those y direction forces in the last example. And so this example highlights how if you change the way that you're looking at the problem, you can get a better idea of what forces are acting, and it gives you an easier time with drawing the free body diagram. So in this case, instead of looking up from above, so if we're having a drone looking down, that was our first example. Now we're on the ground, and it's if you were in the same height as the girl going around in the merry-go-round. And so this is the picture that I have to the right here. And you're standing just where you are, and the girl's going around the merry-go-round like so. So now we want to start by defining our coordinate system. So again, we're going to choose to the left be the positive r direction, so in towards the center of the circle. Now, instead of the t direction for up and down, the up and down will be the positive y direction. So upwards is going to be positive y. And then finally, the direction of the velocity, that tangential direction, that's going to be going into the page being the positive tangential direction, t direction. So we've defined our coordinate system. Now we can draw our free body diagram. This situation's not any different than the first one. We're just changing our viewpoint. So our forces should not change. It's going to change how we label them, but the actual forces themselves are not going to be any different. It's the same physical situation. So labeling my axes, the upwards is going to be the positive y direction. Inwards, or to the left, is going to be the positive r direction, radial direction, or centripetal direction. And we can draw our forces now. So we know we have a weight force downwards in the negative y direction. Weight force. We know we have a normal force acting on the girl from the merry-go-round, and she's not moving up and down, so we know the magnitude of the normal force better be the same as the weight force. So the lengths are going to be the same. So that's F sub n. And then we have frictional force pointing inwards towards the circle. So we have a net force in the radial direction pointing inwards, which is the direction of the acceleration. And that's the force due to static friction between the merry-go-round and the girl sitting down. We don't have to deal with the direction into and out of the page because there's no forces in that direction. And so now we don't even need to deal with labeling in that direction. So this highlights how, depending on how you choose your view, it makes drawing and understanding these free body diagrams a little easier. Now this is looking exactly like how we typically draw free body diagrams. But before, it looked a little different, and it didn't give you as much information just by looking at it.